And so it's my pleasure to introduce Charlie from University of Princeton, and he'll talk about pacifying sufficient connected PSC manifolds, dimensions 4 and 5. Please.
Oh, okay. Thanks. Thanks a lot for the organizers for this chance of giving a talk in the conference. So there's one one thing that I want to say. So I see that my employer in the web page seems to be Columbia University, and so that's why I wrote Princeton here. So there is a Charlie in Columbia, and apparently he's doing number theory. So okay, all right. So today I want to talk about some recent progress on the classification problem of positive scalar curvature manifolds in these particular dimensions 4 and 5, and everything's based on joint work with Oles Chodos and also with Yevgeny Lyubomovich. Okay, let's start with some basic definitions. So scalar curvature is a weak curvature invariant. It's a pointwise function on a Riemannian manifold, and we can think of its value at every point as in some equivalent, several equivalent ways. For instance, by definition, it's the trace of Ricci tensor or the total trace of the Riemann tensor sectional curvature. Or a more geometric way to view it is that it measures the volume of a small geodesic ball. So basically, if you do a Taylor expansion of the volume of a small geodesic ball centered around a point P and write the volume as a function of R, then you see the first order, the first non-zero order of the Taylor expansion is always the Euclidean volume, but the next non-zero order up to a dimensional constant is minus scalar curvature. So in particular, scalar curvature positive at a point means that small geodesic balls will have a smaller volume compared to the Euclidean ball of the same radius. Okay, so unfortunately, this only holds at the level of Taylor expansion. So it cannot, I mean, there's no easy way to extend this equation to a certain, to a definite radius, right? So this is one, I think this is one reason that studying scalar curvature is a little bit difficult compared to some other curvature notions. All right, so in history, there has been this very classical, I think the starting point of many future works is the Custom-Werner theorem. So it is a theorem proved by Custom-Werner in 1975. I think they wrote 3 papers and have a lot of consequences. And a particular one is that if you take a dimension, manifold of dimension at least 3, then basically any smooth function which is negative somewhere can be realized as a scalar curvature function of some Riemannian metric on the manifold. Okay, so in other words, if you say negative scalar curvature or scalar curvature is negative somewhere, then this condition has no topological obstruction at all. I mean, any smooth manifold will have such a Riemannian metric. On the other hand, there are known, let's look at the view from a person in 1975, but then there are already known topological obstructions to the existence of positive scalar curvature metrics. And perhaps the first such obstruction is so-called vanishing of the A-hat genus. So the A-hat genus is a certain characteristic numbers, and in particular, it's polynomial. Its very first version of A-hat genus is a polynomial of the Pontryagin classes. So the claim here is that, well, the theorem here is that if a smooth spin manifold of dimension 4K has a positive scalar curvature metric, then its A-hat genus must vanish. So as an example, let's look at a K3 surface. So this has been a famous kind of manifold. It's a 4 real dimensional manifold, and its A-hat genus is 2. So in particular, it's 2 non-zero. In particular, it has no positive scalar curvature metric. But on the other hand, due to the famous Calabi-Yau theorem, it has a metric with Ricci tensor identically 0, and in particular, the scalar curvature identically 0. So this manifold kind of lies in a borderline. I mean, it's a Custom-Werner. it is one type of custom Werner manifold that supports a scalar zero metric, but not any positive scalar curvature metric. Okay, so this leads to the following interesting question, which is called the obstruction problem, which is simply asking which smooth and closed manifold admits Riemannian metric of positive scalar curvature. So, I mean, I like this question quite a lot because it brings a lot of mathematical tools into study. Okay, so let's start from the basics, namely in low dimensions. In low dimensions, this question is very well understood. For instance, in dimension 2, in dimension 2, scalar curvature is just twice Gauss curvature, right? Then we have a complete classification of which manifolds, which two-dimensional surface admits a positive scalar curvature or positive Gauss curvature metric by the Gauss-Bonnet theorem. So the short answer is that this is the case if and only if the two-dimensional manifold is diffeomorphic to RP, S2 or real projective plane RP2. Okay, so that's the end of story in dimension 2. So raising one dimension higher already creates difficult problems. For instance, in 3 dimensions, nowadays we need to use we have a fairly complete understanding of the closed, which closed Riemann manifolds admit a positive scalar curvature metric. But this need to use, to describe it, we need to use the, conclusion of the Poincare conjecture, for instance. So using Poincare conjecture, we know that each closed orientable 3 manifold has a unique so-called prime decomposition. So in other words, it decomposes as a connected sum of these spherical space forms. So each of these gamma J is a discrete subgroup of SO4s acting on S3. So you have these space forms. And you can also have these S2 cross S1 components in the connected sum. And also you may have these factors which I call Kj, so K1 to Km. Okay, so each of these Kj is a so-called aspherical 3 manifold, and in particular, its universal cover is R3. So you can tell that these Kj's are genuinely different from these spherical space forms and S2 cross S1s by looking at this universal cover. Okay. All right. As a reminder, let's recall that we say a closed smooth manifold is aspherical if its universal cover is contractible. So there are equivalent ways, topologically equivalent ways to make this definition. For instance, universal covers, all the starting from pi 2, all the higher homotopy groups of the manifold and the universal cover are the same. Therefore, the only non-trivial homotopy group of such an aspherical manifold is the fundamental group, and thus the people also, I think, another Euro name, that common name that people call these guys are K pi 1 manifolds. Okay, so K pi 1 simply means the Allenberg-MacLane space. Okay. All right. So we're geometers, so let's look at what kind of curvature conditions we can put to ensure that the closed manifold is a K pi 1. Well, there are easy examples. For instance, all two-dimensional surfaces of positive genus are K pi 1 because by uniformization, they're either covered by R2 or H2, right? Both of them are contractible. And more generally, by the Cartan-Hadamard theorem, if you have a manifold which admits a metric of non-positive sectional curvature, which, for instance, include all the the torus and all the hyperbolic manifolds, then on the universal cover, the exponential map is a diffeomorphism, right? So in particular, the universal cover is diffeomorphic to Rn and hence contractible. Okay, so these are easy examples of smooth closed aspherical manifolds. And let me just say that, okay, and I don't work in topology, but I did a bit of search, and there are various other, non-trivial constructions of aspherical manifolds, much more complicated than these simple examples. So why these aspherical manifolds are relevant to our discussion on scalar curvature? Well, this is due to the following deep theorem by Shen Yang and independently by Gromov-Lawson at around also the same time. So which says that a closed orientable 3 manifold admits a positive scalar curvature metric if and only if there's no asymmetrical component in the decomposition. So let's go back to the prime decomposition here. So basically, Shenyao, Gromov, Lausen says that for such a manifold to admit a positive scalar curvature metric, then necessary sufficient condition is that you don't have these KJ factors in the prime decomposition. And in other words, you see it's just the connected sum of spherical space forms in S2 cross S1s. So equivalent way to describe the result is to say a finite cover of this manifold is diffeomorphic to either S3 or connected sums of S2 cross S1. And of course, a corollary in particular says that the closed asymmetrical 3 manifold does not admit a positive scalar curvature metric. Okay, so so this basically concludes the classification problem up to diffeomorphism in dimension 3, right? So which 3 manifold admits a positive scalar curvature metric. All right, so now the natural question is what we can say in higher dimensions, right? Let's try to develop similar stories for dimension 4 and above. So this turns out to be quite difficult, and it's still unknown in any dimension at least 4. So let me just mention a few landmarks. So first of all, as I mentioned earlier, the first known topological obstruction to the existence of positive scalar curvature metric was proved by Lichnewitz in 1963. So he proved that precisely a 4K dimensional spin manifold has positive scalar curvature, then the A hat genus is 0. So this was this method was based on the so-called Lichnewitz formula and was expanded by Hitchin in 74. Okay, and this already tells us a lot of a lot of manifold does not admit a positive scalar curvature metric. But unfortunately, it leaves the case of N torus open. So N torus, if you take N to be 4K, for instance, it is always spin, and its A hat genus is 0. So one needs more techniques to decide whether the N torus admit a positive scalar curvature metric or not. So it was shown by Shenyao and Gromov Lausen around 80s that the N torus indeed does not have any positive scalar curvature metric. And as a remark here, important remark here, the theorem also holds for the N torus connected sum with any closed manifold M. Let's say the dimension, well, let's say either M is spin or the dimension N is less than or equal to 7. So why this is important is that this implies via the so-called Lohkamp reduction, the positive math theorem for symptotically flat manifolds in this dimension N. Okay, and just to diverge a little bit from the main topic. So let me just mention that last year we also extend this theorem in low dimensions. Well, sorry, I should have wrote here. So N is less than or equal to 7. So in dimension less than or equal to 7, if you take a manifold torus connected sum with M, where M is not required to be closed, then we also know that this manifold does not have any complete positive scalar curvature metric. Okay, so a natural wonder is whether this, also you can play the trick of Lohkamp reduction, whether this result implies the positive math theorem, but it actually turns out a bit tricky if you allow M to be non-compact, and this is actually done this year recently by Lizard, Unger, and Yao, where they proved a version of positive math theorem on symptotic short-shield manifolds with arbitrary ends. So you should imagine this manifold has 2 ends. So one end is asymptotically short-shield, and the other is arbitrary. So you only know the metric is complete. Okay, so and their positive math theorem works on such a manifold. And I believe Martin Lizard is actually going to give a talk in this conference tomorrow on this result. All right, so let's continue the discussion. Well, by the way, any questions so far? Okay, cool. So let's continue the discussion. So in dimension 4 and above, what other things can we say, right? So let me mention two other landmarks. So for instance, Gromov-Lausen started this project in 80s, and Stolz completely finished this in 92. So they gave a categorization of simply connected manifolds of dimension at least 5, which admits a positive scalar curvature metric. So this categorization is in terms of the differential structure, right? So it's not quite the same as this three-dimensional case where we can write down the list of all such manifolds in diffeomorphism. So their conclusion is basically a simply connected manifold in dimension at least 5 admits a positive scalar curvature metric, if and only if either the manifold is non-spin or it is spin and a certain invariant called the alpha invariant vanishes. Okay, and how about dimension 4? Well, actually, in dimension 4, discovered by Witten in 94, there's another invariant which obstructs the existence of positive scalar curvature metric, and that's the Seiberg-Witten invariant. Okay, so as you can see, there are quite a lot of mathematics going into the in the history of study. Okay, so the first problem in general dimensions, including 4 and above, is the so-called K-pi1 conjecture. Well, people, I always hear people say it's the Gromov-Lausen conjecture, but I can't quite find a reference. But on the other hand, Shen Yao does wrote down this conjecture in 1987. So it's saying that the closed aspherical manifold does not admit any Riemannian metric of positive scalar curvature. So apparently this is known in dimension 2 and 3 and not in higher dimensions. Okay, I want to talk about some other related problems in scalar curvature, and one closely related question is a much more ambitious formulation of the same problem, namely this aspherical conjecture in the form of metric geometry. So this is written in the paper by Gromov called large Riemannian manifolds. So let's for now skip the definition of the large, the largeness. But the claim is that the conjecture is that if you have if M is a large Riemannian manifold, then for any radius, so this R is a radius, any positive radius, the supreme of a volume of geodesic ball is bigger than or equal to the corresponding Euclidean volume of the same radius, of the ball of the same radius. Okay, so let's remember that scalar curvature, and the sign of scalar curvature decides whether your volume of geodesic ball is larger or smaller compared to the Euclidean one, right? At least for the small radiuses. So in particular, if let's say your large Riemannian manifold is complete and has bounded geometry in a certain sense, then this volume comparison for all the small radiuses would imply that the infimum of scalar curvature is less than or equal to 0, right? For any point. Okay. So now let's go to the largeness, the notion of large Riemannian manifolds. So Gromov didn't give precise definition of what largeness means, but he does give quite a lot of examples, a class of examples where this manifold should be large. For instance, one such class is the class of complete contractible Riemannian manifolds with an isometry group acting co-compactly on M. Okay, so let's unwrap these words a little bit. We have complete class and contractible, and you would have an isometry group such that the fundamental domain of isometry group is compact. So in particular, if you take the universal cover of a closed aspherical Riemannian manifold, then by definition, this universal cover is large. Okay, so in particular, conjecture B says that on the universal cover of a closed aspherical manifold, the infimum of scalar curvature should be less than or equal to 0. So in fact, this conjecture B is a stronger version of conjecture A. All right, so let me also mention some other relations with metric properties and topological properties of positive scalar curvature metrics. First of all, Rosenberg in '93 proved that if a form of strong Novikov conjecture holds, then the asymmetrical conjecture holds, the K-pi1 conjecture holds. Okay, so in my understanding, the Novikov conjecture has, you can work with several different coefficient, coefficient rings, but if a certain choice of those rings and works for the Novikov conjecture, then the K-pi1 conjecture holds. Okay. All right, and there are also connections between the K-pi1 conjecture and other metric properties of Riemannian manifolds with, let's say, scalar curvature, strictly positive lower bounds. For instance, this include the Iverson width property, the so-called width, and the filling radius. So these are all purely metric notions, that there's no curvature involved. Let me show you one such example. Simply, this is about the notion of the Iverson width. So the formulation is the following. If you have a complete Riemannian metric with, let's say, scalar curvature bigger than or equal to 1, then there should be a dimensional constant Cn and a minus 2-dimensional simplicial complex, and a continuous map from your manifold to the simplicial complex, such that for any point on the simplicial complex P, the diameter of its pre-image is bounded by, the dimensional complex. Sorry, the dimensional constant. Okay. All right. So this basically says that a manifold with scalar curvature, positive scalar curvature, roughly speaking, looks like a minus 2-dimensional simplicial complex, right? In a metric geometry sense. Okay, so all these conjecture A, B, C's are kind of connected with each other. And also, I believe this conjecture C about the Iverson width would also imply the aspherical conjecture. So conjecture A is actually the weakest among the three, okay, and it should be the easiest. Are there any questions so far? Okay, let me continue. So there are various previous progress. So let me just mention a few of them. First of all, when the dimension is 4, in a survey paper in 1987, Shen Yao, in the same paper, Shen Yao proposed this conjecture, the K-pi1 conjecture. They actually also proposed an outline of the conjecture in dimension 4. Okay. Well, it's an outline, so essentially there's no detail of or any rigorous argument, but this outline is very important and inspirational. And later in 92, Green and Peterson proved a very local and very coarse version of conjecture B. So remember, conjecture B is about volume of geodesic balls. And Guo Liangyu in 99 proved the conjecture A holds if the universal cover of M has sub-exponential volume growth. And his result was extended by Trenishnikov in 2002. Okay, so maybe I'll put a comment here that both results and there are various other, these kind of results are based on the connection with Novikov conjecture. So I believe Guo Liangyu actually proved a certain form of Novikov conjecture with this sub-exponential volume growth condition. And a quite a great breakthrough was done by Larry Guth in 2011, which says that the following weak version of conjecture B holds. So for any radius R, positive radius, the supreme of volume of geodesic ball is bounded below by a dimensional constant times the Euclidean volume. Now the dimensional constant could be quite small, but still, I mean, it's uniform in OR and in all manifolds. And Jian Wang in his PhD thesis in 2019 proved the K-pi1 conjecture for 4 manifolds with positive first Bettian number. Okay, so his proof is based on the minimal surface and dimension descent argument. And that, let me just comment that there are infinitely many different spherical manifolds in dimension 4 with B1 equal to 0. And conjecture 3, remember the conjecture about the n- dimensional simplex and simplicial complex and Uritzen width. So it is actually done proved in dimension 3 by Lukamovich and Maximum. Okay. All right, so there are various progress in these directions. So let me tell you some of the recent progress. So first of all, last year, joined with Otis Chodos, we proved that the K-Pavan conjecture holds in dimensions 4 and 5. So basically a closed spherical manifold in these dimensions. On such a manifold, the only metric with non-negative scalar curvature is the flat metric. Okay, so in particular, it does not admit a positive scalar curvature metric. Okay, and a remark here is that Gromov also proved the result in 5 dimensions independently. I think our paper and Gromov's paper are based on certain similar ideas, but we obtained this result independently. Okay, there's also a more general mapping version of the theorem that I'll give you in a minute. Okay. So in dimensions 4 and 5, we know this non-existence result that as closed as spherical manifold cannot have positive scalar curvature metric. And we sort of wanted to turn this result into a positive result, namely, in some sense, we would like to classify positive scalar curvature manifolds in these dimensions. So we're able to do it under these additional conditions on higher connectivity. So basically vanishing of higher homotopy groups. The statement is the following. So this is joint work with Otis Chodos and Yevgeny Lukamovich this year. So what we prove is that if you have a closed manifold with positive scalar curvature in dimension 4 and 5, and you assume pi2 is 0 in dimension 4, or pi2 and pi3 are both 0 in dimension 5. Then the conclusion is that the finite cover of such a manifold is homotopy equivalent to Sn, or connected sums of Sn minus 1 cross S1. Okay, here are some remarks about some various points in the theorem. First of all, one wonders, okay, so remember the 3-dimensional result is classification up to diffeomorphism. So whereas here you see we only get homotopy equivalent. So that's, I would say, not satisfying. Well, in dimension 4, if you know that this finite cover n hat is homotopy equivalent to S4 or S3 cross S1, or in dimension 5 without any further assumption on the homotopy type, this theorem, the result of this theorem can be upgraded to homeomorphism. So I think our approach can, the best hope of this kind of approach can give you homeomorphism. So for diffeomorphism, we still need a much more delicate approach, like, I don't know, maybe a flow approach would be more relevant here. Okay, and the second remark here is that the conditions on higher homotopy groups are necessary. Okay, so without, for instance, without pi2 equals 0 in dimension 4, this conclusion is definitely false. And the typical counterexample would be a K torus cross a sphere in the complement dimension, and let's say K is less than or equal to n minus 2. Okay, and the reason is very simple because a dimension, a sphere of dimension 2 or higher admits a metric with arbitrarily big scalar curvature, right? So you can cross it with any manifold to get a positive scalar curvature manifold. Okay, and heuristically, so if you remember conjecture C, the positive scalar curvature condition on an n manifold would imply, without any homotopy group conditions, the positive scalar curvature should imply that the Urisohn dimension, the n-2 dimensional Urisohn width is finite, right? So it's bounded by some dimensional constant. Now, as we will see later in the proof, this result, is based on the following fact, or you can also, I guess you can also see it from the statement here. So this result here says that the Urisohn dimension of this n hat, or the universal cover of n, is actually equal to 1. So in a way, we can construct a map from the universal cover of n to a one-dimensional simplified complex, namely a graph, right? We can construct such a map with diameter bounds of any pre-image. Okay, so this is why I wrote here that heuristically, assuming these higher homotopy groups vanish, this implies that the Urisohn dimension of this manifold will decrease. Well, right. So n-2 would be the most general one, and if you assume some pi k's vanish, then you could decrease from n-2 eventually to 1. So, well. So I think that there may be a more general, much more general statement on this kind of fact. And any questions so far? Okay. There's also a kind of interesting connection with another kind of curvature condition, which is the so-called positive isotropic curvature. And a big conjecture for this kind of curvature condition is that if you have a closed manifold with positive isotropic curvature, so the peak condition, then the fundamental group should be virtually free, and in fact, the finite cover is diffeomorphic to the connected sums of the spheres and Sn-1 cross S1. Okay, so this is the fundamental group part is conjectured by Gromov, and the diffeomorphism type was by Shen. Okay, so there were previous approaches towards this conjecture, include the minimal surface techniques by, for instance, Michailov, Moore, and Fraser, and etc. So in particular, we know some kind of connectivity condition, namely, sorry, it should be pi2 here. Okay, sorry. Namely, starting from the second homotopy group pi2 all the way to the homotopy group of n over 2 should be 0. Okay, and there are also Ricci-Flow approach independently by Brandel, Shen, Brandel, and Qiantang, Zhu, and Huang, etc. And towards this conjecture, and in fact, Ricci-Flow shows that the conjecture holds in dimension. Oh, sorry, I made quite a few typos on the slides. So they prove this in dimension 4. So in dimension 4, peak manifold, up to a finite cover is diffeomorphic to connect sums of S3 cross S1 or S4. Okay, and in dimensions at least 12. Okay, so this is done by Brandel and Huang. So an interesting question here, if you compare our theorem and the condition that the peak condition actually implies positive scalar curvature. So the question here is that in 5D, does peak imply pi3 of the manifold is 0? Well, if this is the case, then what we can prove is that actually at least pi1, the fundamental group part of the conjecture is true, and the Shen conjecture is also true if you replace diffeomorphic to homeomorphism. Okay, so as I mentioned, there's also a more general mapping version of such theorems, and the statement is the following. So let's take the same dimensions 4 and 5, and there are more. There are two manifolds in this kind of theorem. So first of all, you take a closed arrangable manifold with positive scalar curvature, and that's called X and G. And you also take a closed arrangable manifold n in the same dimension, and suppose that there's a map from x to n of non-zero degree. Okay, and on the target manifold n, we put the same higher connectivity condition, namely pi2 is 0 when dimension 4, and pi2 and pi3 are both 0 when dimension is 5. Then the fact that there's a non-zero degree mapping from a positive scalar curvature matrix tells us that the target n satisfies precisely the same condition, namely a finite cover is homotopy equivalent to sphere or connected sums of Sn minus 1 cross S1. Okay, so in particular, this tells us that the following kind of corollary. So one typical example of such manifolds n are aspherical manifolds. So in particular, if we have a closed arrangable manifold admitting a non-zero degree map to a closed arrangable k pi 1 in the same dimension, then this X cannot admit any positive scalar curvature metric. Okay, so I want to mention here that this corollary I think is also claimed by Gromov in his latest version of the lecture notes in scalar curvature. And let me maybe just mention one last thing before we move into a bit technical part. So there's also a version of this, both the theorem and the corollary of possibly non-orientable manifolds. So basically, if you replace orientable by non-orientable everywhere, and then the mapping F is assumed to be of non-zero mod 2 degree, then the same conclusions hold. Okay, so any questions before I move into proofs? Okay, so let me try. Yes,
excuse me. There is a question in the room.
If the F is smooth or just a continuous enough, the map from X to N is a map with a non-zero map. So I want to ask the map is a smooth or just a continuous map.
Well, okay. First of all, I think in the closed, if both the domain and targets are closed, then any continuous map can be approximated by smooth maps of the up to a very arbitrarily small error. So it doesn't matter basically.
Okay, thank you.
Yeah. Okay, so let me motivate a little bit of the proof and try to tell you some of the key ideas. So the starting point to prove the k pi 1 theorem is the following. So okay, this lemma here is has a 5-line statement, but really describes the following phenomena. Now, if you take a closed Riemannian manifold and assume its universal cover is non-compact, okay, so we're living in the universal cover, so I'll draw pictures. Then you can always do the following thing. So you can always, first of all, take a geodesic line. It's called sigma. So this is a geodesic line. Namely, it's a mapping from R to the universal cover such that the distance between any 2 points on sigma is equal to the difference in the parameter. Okay. Now, and also you can take a intersecting hypersurface. So this is our m hat. So this is m hat n minus 1. So this is a minus 1 dimensional hypersurface, such that the intersection of, first of all, the intersection of sigma and m hat is non-zero algebraically. Okay, non-zero algebraic intersection. And second, the distance between the boundary of m hat and the sigma is bigger than, let's say, 3L for arbitrary L. Okay, so actually we can fix the choice of geodesic line and take this m hat larger and larger. Okay, so a typical picture to keep in mind is that in Rn, the Euclidean space, sigma would be the xn axis, and m hat would be the disk of radius 3L on the x1 to xn minus 1 plane, or hyperplane. All right, so the key step, let's say at least for the three-dimensional aspherical theorem is the following theorem by Shen and Yao. And I want to call it a homological filling estimate, and you will see why. Okay, so the theorem says that if you have a two-dimensional surface, sigma g, with this spectral condition that lambda1 of minus Laplacian plus k is bigger than or equal to a positive constant kappa over 2, then basically your manifold sigma the surface sigma cannot be too large in the following sense. So if sigma has no boundary, then the diameter is bounded above by 2 pi over square root of kappa. And if the surface sigma has boundary, then the distance between any point on the surface to boundary is bounded above by the same constant. Okay, and this lambda1, I should have mentioned that is with a Dirichlet boundary condition. So you look at the first Dirichlet eigenvalue. All right, so this is a very nice theorem, and if you're unfamiliar with such a statement, this extends a classical result by Bonnet-Meyer. Right, Bonnet-Meyer says that the same conclusion holds if you assume the surface has Gauss curvature bigger than or equal to kappa over 2. Okay. So apparently Shen Yao is, the lambda1 condition is an extension of the lower bound of Gauss curvature condition, and they use this spectral lower bound to derive the same conclusions. All right, then the theorem has the following consequence. So in a three manifold with, let's say, scalar curvature bigger than or equal to 1, you take a non-homologous curve inside. Then the curve, of course, is non-homologous, means it has to bound a two-dimensional surface. But then the curvature scalar curvature lower bound tells you that the surface has to live inside a 2 pi neighborhood of this curve gamma. It can't go too far away. And why is that? Well, the reason is basically the following. You can solve the plateau solution sigma with boundary gamma. Namely, you take the homologically error-minimizing surface with the boundary, and then the stability inequality of minimal surface tells you that the following inequality, your stability inequality is true for any compactly supported C1 function. And now you use the condition that scalar curvature is bigger than or equal to 1, and this is square term a squared, so it's bigger than or equal to 0. Therefore, you get you derive the spectral condition that lambda1 of minus Laplacian plus k on the surface is at least 1/2. Okay, and then you use a Shen-Yao theory. Okay, so this proposition is the so-called, what I would call the homological filling estimate. So namely, non-homologous means that you can always fill in by a cycle of one dimension higher. But with the curvature condition, you can further say that the fill-in is bounded in distance. All right, so combine this, the previous lemma and this homological filling estimate, we can give a very short and simple proof of the three-dimensional aspherical theorem. Namely, let's try to prove that the closed aspherical 3 manifold does not admit any positive scalar curvature metric. So the proof here is different from the original proofs of Shen-Yao and Gromov-Lawson, but it does extend to higher dimensions. So I'll give you a proof by picture, and instead of showing you the words. So remember, we can find geodesic line. Oh, okay. Sorry. First step, we pass to universal cover, and we find a geodesic line sigma together with a surface. So I'll draw the boundary of the surface here. So this is a surface. Let's call it m hat, right? Remember, it's a two-dimensional surface. And such that, first of all, its algebraic intersection with sigma is non-zero. And second, its boundary is sufficiently far away. So let's say here we take the distance to be bigger than 2 pi. Okay, now let's say gamma is the boundary curve. So we apply the previous proposition, Namely, by taking the plateau solution of gamma, we can always find another surface. Let's say this is a sigma, such that sigma is living inside the 2 pi neighborhood of the curve gamma. Now, by directly comparing distance, you know that in particular, this means sigma does not intersect, well, the geodesic line, little sigma at all, right? Because of the distance restrictions. Now, the observation is that if you put the union of M2 and the surface sigma, you see they have the same boundary, so their union is boundaryless, right? It's in particular, it's a 2 cycle. Therefore, this 2 cycle intersect sigma, the geodesic line, non-zero algebraically, right? Because M hat intersect algebraically and the other surface sigma does not intersect at all, right? Okay, that's a contradiction because this would mean that the 2 cycle M2 union with sigma is non-trivial in homology. Okay, so this is a contradiction, right? Because the universal cover of a spherical manifold should be contractible. All right, so this is the formal proof. Now, let's move into higher dimensions and see what kind of conditions we really need and what kind of estimates it's necessary. Now, let's take, in general, an M manifold closed and as in the theorem 2. So remember, in theorem 2, we assume that pi 2 up to pi of M minus 2 of the manifold is are all 0. Now, taking the passing to the universal cover, pi 2 and up to pi M minus 2 are the same for the universal cover, so also 0, and pi 1 of universal cover is also 0. Therefore, by the Hero theorem, the universal covers first M minus 2 homology groups are, integral homology groups are all 0. Okay, so the key estimates is the following homological filling estimate analogous to the one in dimension 3. So basically, the statement is that in dimension 4 and 5, there's always some big constant L depending on the closed manifold, such that for any integral M minus 2 cycle, there exists an M minus 1 cycle, M minus 1 chain, such that this M minus 2 cycle is the boundary of the M minus 1 chain. And moreover, the sigma M minus 1 is contained in the L neighborhood, tubular neighborhood of its boundary. Okay, so if you are let's try to see that this is actually a higher dimensional analogy, right? If n is 3, then this is a 1 cycle, so a curve, and you can write it as the boundary of a 2-dimensional chain. Okay, so the proof of the theorem is the most difficult part, so I'll try to skip that, but instead I'll try to give you some consequences. Now, first of all, by combining this estimate and the previous lemma regarding existence of geodesic lines and intersecting hypersurface, we can prove the spherical conjecture just as before, right? Take the geodesic line, take intersecting hypersurface whose boundary is at least L, strictly bigger than L away from the line, geodesic line, and then fill in by sigma M minus 1, and you obtain an M minus 1 cycle intersecting the geodesic line non-zero algebraically, right? Contradiction. Okay, I'll try to conclude everything in 5 minutes or so, and So the spherical conjecture is proved fairly easily using the homological filling estimate. And let me try to tell you how do we prove the classification result in dimension 4 and 5. So the starting point is the following observation inspired by a work of Albert Bielski and Guth, which we learned from a talk. So basically, we can prove the following thing. So assume that the manifold NG has the above homological filling estimate, namely any integral M minus 2 cycle in the universal cover can be filled by its L tubular neighborhood. Then the universal cover satisfies the particular property, namely for any fixed, for any point P in the universal cover, each connected component of the level set of the distance function to P has diameter less than or equal to 20L. Okay, so let's try to understand this, this property a little bit. So the distance function is, of course, a continuous function from the universal cover to the real line. Now, the real line is a very simple one-dimensional simplicial complex. So this says that, this proposition says that, well, basically, the universal cover has Urisohn 1 width less than or equal to 20L. Okay, so the homological filling estimate actually tells us that the universal cover's Urisohn dimension is 1, and the Urisohn 1 width is bounded by 20L. Okay, so with this in mind, let's try to prove the topological consequence. The proof consists of 3 steps. Some of them are, purely topological, and some of them are geometric a little bit. So the first step is a suitable covering argument. So basically, we use the above proposition that, regarding the distance function to show that each finally generated subgroup of the fundamental group cannot have only one end. So the end here is a notion related to geometric group theory. So basically, the number of end of a group G is defined as the number of end of covering space K, where K is covering space of some other simplicial complex K, K2 covers K, and the G is the group of covering transformation. Let's say DAG transformations. Okay, so to give you some examples and also to relate to the scalar curvature problem, let's see the number of ends of the group Z. Let's look at the group Z. Okay, so I claim this is equal to 1, and why is that? Well, because we can take the covering R cover S1, right? So then the group Z is the group of DAG transformation, and of course, the number of ends of the group Z is 2, and then the number of ends of the manifold R is 2, right? Because if you dig out a large enough interval, then there are 2 connected components. And similarly, the number of ends of the group Z2 is equal to 1. And why is that? Well, because you can take the covering R2 covers T2. And so the number of ends of R2 is equal to 1, right? R2, the plane is connected once you dig out a sufficiently large ball. So basically, we the observation is that this the distance, the previous proposition regarding the level set of distance function tells us that such phenomenon can never happen. So basically, any subgroup, finite generated subgroup of the fundamental group cannot exactly have one end. Okay, so we proved this inspired by a work of Ramachandran and Wolfson. So using this and some classical geometric group theory due to Serre and Stolling and Dunwoody, we can actually prove that pi1n is virtually free. So virtually free means that it contains a finite index subgroup, which is a free group. Now, of course, the free group is the fundamental group of these wedge sums of S1 or connected sums of Sn-1 cross S1, right? So in the final step, we apply a purely topological result by Gatgill and Sasatri. So which shows that if you have a closed manifold such that pi1n is a free group with k generators and you have certain higher connectivity condition, then n is actually Helmholtz equivalent to the connected sums of k copies of Sn-1 cross S1. Okay, so to apply to our situation, we take the manifold n, we pass to the finite cover corresponding to this finite index, okay, then the finite cover will have a free group as its fundamental group together with all the, pi2 to pi n minus 2 are all vanishing. Then this theorem of Getgill successfully tells us that the homotopy type. Okay, so this is all I want to say today, and thanks a lot for the attention.
Thank you, Chao. So I guess there are plenty of questions, either in the room or in the chat or directly. Okay. Do you have any question here? Okay. Okay.
Yes. Can you recall the hypothesis which makes the whole strategy work? Because I forgot the exact hypothesis.
I'm sorry, I didn't hear clearly. So which strategy?
So you're asking for the hypothesis. If you could recall the hypothesis.
Recall the hypothesis, please.
Hypothesis. Okay. Let me here. So base. Yeah. Sorry.
Okay.
Here. Oh, wait. No. Yeah. This one. So basically, we require the homotopy group from pi2 to pi n minus 2 are 0.
And for the group being virtually free, it is what are the hypotheses?
Oh, virtually free means I'll just write here. So virtually free.
Yes, but what are the hypotheses which makes this group virtually free?
So are you asking the definition of group being virtually free?
No. The hypothesis of the theorem whose conclusion is the group is virtually free and other conclusions.
These are not you don't need all these hypotheses in order that the group should be virtually free, I think. No?
We do need to use all the conditions here. No, we do need to use it.
Okay.
Yeah.
Yeah, because if he has the torus, then right, you would, if you have a torus inside it, then you would have a abelian group.
Yeah. So basic counterexamples are as here, right? The torus cross S of n minus k, and you have a torus factor. The fundamental group will contain a z, direct sum z, for instance. That's not a virtually free group.
Okay, more questions?
Excuse me, can I ask? So it's maybe
two questions, Sasha.
So it's something very simple, probably. So there was a geometric comment, so that if you have manifold with some condition, then the universal covering contains a line and so a cycle far away from it.
Far away?
Far away from it, so that its feeling intersects this line. So does it always hold if the universal covering is constructible, or what do you need?
Well, yes, good question. So that's well, you can find a good reference for that is Chigger-Gormal, the classical splitting theorem. So basically, the fact that it is a fact that any non-compact universal cover will contain a geodesic line.
Yes, that's a simple, yeah. Okay.
Yes, and then well, you can just take we also wrote this construction in our paper. So then you can basically take the intersection of okay, so you can take the -2 cycle as following. So you first take the boundary of a tubular neighborhood of that geodesic line, and then you take a point on the on the line and take the large geodesic sphere around it. The intersection of the tube and the sphere is a -2 cycle far away, which intersect non-zero. Yeah.
Okay. So it's simple. And you only, so what kind of condition do you need? So are there some
non-compactness? I think it's we didn't need to use contractibility.
No, but if you only have non-compactness, so then you take S1 times Sn minus 1, then the universal covering is line times sphere, and then you cannot go too far away from the line. So you need to be able to go away from the line. So but contractible, yeah. So if
well, okay. I think, yeah, let's see. Wait, so your example is S1 cross Rn minus 1?
No, S1 cross Sn minus 1.
I see. Okay.
Then the universal covering is,
right. Yeah.
Yeah, the universal covering is line cross a sphere, and then you cannot go too far away. So that's, but probably
I see.
If you are so it's contractibility probably, yeah. What?
I see. Okay. Yes. Thanks for the comment. Yeah. Good point.
Okay. Yeah. Okay. Thank you.
Any more questions?
How to get the end of the fundamental group has a one end from the homology fitting properties.
Right. So basically I'll just show you why the fundamental group itself cannot have only one end. So the reason is the following. So now if you take you take this okay, so suppose let's see how it works. So suppose you have only one end, then take let's see. Okay, so let's still take a geodesic line, because the geodesic line always exists. Okay, so and take the point P on it. Now, if the universal cover has only one end, this means that you take this point far away. Let's say Q1 and Q2. These they would belong to the same connected component of the complement of a big ball centered around P. Right. But then since Q and Q2 are on the geodesic line, this distance here is huge, arbitrarily large. So this is a contradiction.
Okay. Yeah, thank you.
And your construction for the geodesic line is kind of like Cheeger.
Yeah, it's exactly
where you're just taking actions of the points and extending longer and longer.
Yeah.
Very good. I guess there's no more questions. So I thank you so much for this beautiful lecture on scalar curvature, Sharon. And we'll resume in 25 minutes, actually. See you soon.
Thanks.
Bye-bye.
Bye.